Hi, Paul. Am I audible? I think you're mute right now.
Okay. Hello.
Yeah. Hi, Paul. I'm Arun. I'm a team lead along with Balaji here.
Hi, Paul.
I hope we are visible to you.
Yeah, I've got a couple of pictures on the screen.
So, we are Team Abhyuday. We are the rocketry team of IIT Madras, India, the Indian Institute of Technology, Madras. We are the first one in India to develop a hybrid rocket engine. So, we are the first application from India to participate in the hybrid category. And yeah, we recently had our static fires done, and we are in the final assembly process.
You've got a big bit of an echo. I don't know if you've got two microphones going or what's going on, but
Is it fine now?
um,
Was this
there's some bit of an echo. But let's go ahead and try. Thank you.
just give us a second.
Yes, sir.
Uh, Paul, can you hear me right now? Hello. Paul, can you hear me right now?
Hello.
Yeah. Can you hear me right now? Is my voice clear right now?
It seems clear, yeah.
So, good evening. I'm Balaji, and I'm one of the leads of the team. So, as Aryan was mentioning previously, me and Aryan, so we both are currently the leads of the team. So, let me first introduce about ourselves. If my audio is clear, I'll go ahead and do a formal introduction of the team. Is my audio clear?
Uh, do what? I'm sorry.
If my audio is clear, I'll go ahead and do a formal introduction of the team.
That'll be fine.
Yeah. Uh, so, good evening. We are Team Abhyuday. We are the rocketry team from Chennai, India. IIT Madras is our institution. So, we are the first Asian student team to develop a hybrid rocket engine. And Spaceport, this edition of Spaceport, is our third participation in the competition. So previously we participated in two editions of Spaceport, the 2023 edition and the 2024 edition, where we flew with 10,000 feet squads. So we flew with commercially off-the-shelf motors twice previously in the past two editions, and this edition is our first entry in the hybrid category. So now we are aiming to participate in the 10,000 feet hybrid category. So like to shine light on our backgrounds, in 2023 edition we finished around 16th in the Barrowman rank. That was our first entry in the competition. The rocket was named Chetak 1 and we were targeting 10,000 feet. We flew with a Red Lightning motor. And in the 2024 edition, I mean the last year's session, we were first in Asia, I mean across all categories. And in terms of like the entire competition, we were 11th in the 10,000 feet category. In the 10,000 feet category, we were 11th. So these were our previous experiences handling with the competition. In the previous year, we also implemented a rocket with a minimum diameter the diameter of the lower body tubes is like the same as the engine's diameter. At the same time, we implemented a canard system. So what happened in our first year's launch was the rocket had excessive roll. So we tried to implement a canard-based roll control system in our last year's participation. At the same time, we also had an ESRA avionics bay. So we developed a flight computer on our own over a span of a year, and over the last year's edition, we flew with the avionics bay. So coming up for this year, what we have online is we have an engine fully developed by us, fully developed by our student team, which is a hybrid engine of paraffin wax and nitrous oxide combination. Then we have an updated version of our last year's flight computer. The flight computer that flew on our rocket last year has been updated, and we are participating again. I mean, we are having again a startup avionics bay. At the same time, last year we had a reefing-based recovery system. We are going ahead with the same this year. Instead, last year we had a black powder-based reefing recovery system. This year we have a carbon dioxide canister-based recovery system. And then at the same time, the canards bay, as I mentioned, it didn't perform as expected over the last year. We had a failure in our canards bay. So we made some modifications based on whatever we learned over the last experience. And we are flying this year with a modified canard bay. So this is roughly what we've been trying to do and what we are aiming at for this year's competition. And we have a camera titled Anjana, if you can see it. Anjana, can you make it landscape instead of portrait? Auto rotate on. Can you enable auto rotate? Can you see a camera titled Anjana? Is that clear?
Yeah, I can
Yes,
see
so
it.
you can see the nose cone. So let's come from the top to bottom. We have a metal tip from the nose cone at the top. Then coming to, we have a one common profile. Anjana, you can just come back a little. Yeah, so over here sitting beside the nose cone is our payload. So we have a payload system which is titled the Aetorium. What we are basically trying to do is when we are recovering the rocket back, when the rocket is coming back with the help of parachute, we are trying to take in air through suctions, sample the constants of the air, and then send it out. So this payload you can see over here, which is in form factor of a 3U, is going to perform that task for us. And then, Anjana, can you focus on the canard system once? You can go to the other side of the table. Yeah. You can make it landscape and move a little back. You can relax out, it's fine. You can see a canard and air brakes bay over here. If that's clear, can you just confirm if that's clear to you in the video?
Yes, I can see it.
So we have a canard bay, which is a modification of last year's bay. So we try to do some changes. Just a minute. Yeah. Can you hear me right now?
Yes, I can.
Yeah, so the canard bay is a modification of last year's bay. Last year's canard bay failed, as in the canard snapped off after a few seconds of launch. So we realized why that happened and we made some structural modifications. At the same time, we also updated our software, basically the way in which you're predicting the roll and the way in which you're controlling it. Apart from the canards, we also decided to implement air brakes in this year's rocket. So the flaps you can see over here next to canards are for air brakes. So this is the canard and air brakes way. Now, Anjana, can you move back a little and zoom out? Yeah. Following that, we have our recovery base. Above the canard bay, we have our payload bay. Then we have our avionics and recovery. And Anjana, can you come to the oxidizer tank right now? Over here, we have a nitrous oxide oxidizer tank. And if you can come back a little more, we have a lower structure which will house the engine, and then we have our fins of the rocket. So for this year's element, fins currently are filleted at the moment. We are yet to perform a tip-to-tip layup of the fins, which we are about to do in the next couple of days. And at the end, we have a boat tail made out of aluminium. So the rocket is primarily made out of carbon fiber. The internal couplers are made of glass fiber. Engine is made of aluminium, and the tip of the nose cone is made out of aluminium. Now, if the externals and like the brief overview is clear, we can dig into each vertical. We can come from top to bottom, and like we can detail everything about the rocket.
Okay.
Yeah. Okay. I would suggest Pritish to. I have a team member here, Pritish. So he'll start with the airframe and then like the internal layout first. Just a minute.
One second, let me just share my screen. Can everyone see my screen?
Yep.
Yeah, so this is the open rocket file in which we have designed the. Oh, am I not audible? I am audible. Okay, so this is the open rocket on which we designed it. So the like Balaji mentioned, the nose cone is of a one carbon profile with a fineness ratio of 5, and it's given a wall thickness of 0.25 m, 0.25 centimeters, 2.5 mm, which is regular for any kind of composite that you go with. And like Balaji mentioned, the tip is aluminum for easier manufacturing. Then uh, the nose cone, yeah, the tip is about 25 centimeters in length, and there's a nut inside the nose cone which holds the tip in place. So inside the nose cone is where we'll be having our payload. About the nose cone, after the von Karman profile, we have extended it by 30 centimeters. And on the 30 centimeters, there's a coupler. The outer dia of the coupler is around 155 and inner dia of the coupler is 150. So the coupler is also again uh, 2.5 mm thick. And on the coupler, 5 centimeter from the edge of the airframe, that is the nose cone, we have a payload bulkhead. Anjana, show the payload bulkhead. Payload bulkhead. So that is a payload bulkhead that we have designed on which our payload would be sitting. This is, we also have cut edges so that we can epoxy nuts onto the other side while we are integrating with the coupling the two tubes. So yeah, going down from that, we have our canards bay, which will be further covered upon by the control steam, and below which we will have the air brakes. And going below that is where we have a recovery bay. As you can see, there is the coupler over there. That is the point of separation for the rocket. The bay is about 53 centimeters in length, and it will hold a 12 feet rocket man parachute. So the deployment, it's a single deployment, but dual event. So the at Apogee, the parachute will be deployed using CO2 canisters as main, and then we also have a redundant pyrotechnic charge that we will be using to deploy in case our CO2 mechanism fails. So on the table we can see the parachute packed along with this thing, reefing wire and shock cords. And also on the bulkhead, we have our recovery system, the CO2 recovery system, and another tube for keeping our pyrotechnic charge. And below this whole assembly is where we'll have our rocket avionics. This consists of our COTS and SRAT both, and below which we'll have our aux tank and the vent assembly. Below the aux tank is where we'll have our engine and our feed assembly, and the fins of the rocket are right now just surface mounted, as in they have a 2.5 mm thick thin slab that will just go in, and right now it's filleted. And for strength reinforcement, we are using about 4 layers of CF to reinforce it. So tip to tip layer. And
Okay.
for retention at the back end, we will have a bottle. So this is the complete overall look of the airframe and the recovery systems. If you have any questions, just let me know.
Where your electronics are located, what is the airframe made of?
Oh yeah, so the nose cone and the engine housing, that is the foremost end and the aftmost end. Both of them are carbon fiber. The fins are carbon fiber. The two tubes, that is in the middle, the recovery tube, what we call the recovery tube, and what we call the avionics tube, they are both glass fiber. All the
Okay.
couplers inside are also glass fiber.
Okay. I just want to make sure that you didn't have carbon on your electrics.
Yes, yes.
Yeah, I know it's something that you should know, but just want to make sure. Okay.
Okay.
Uh,
I will.
Go ahead.
Yeah, I will hand it over to controls.
Okay.
Go ahead.
Hello, can you guys hear me? Yeah, so hi Paul. So this is the control system for rocket. So as Balaji mentioned previously, last year the canards sheared off at max Q. So to counter that, this year we've added bearings and we've made a custom holder for the bearings, as you can see. I'm gonna zoom in on that adapter. Yeah, so as you can see on the canards, there are bearings attached to support the loads that it will experience during max Q. So all the loads will be taken care of by the body tube. So below this, there's a bulkhead to hold all the canards, electronics like the servos and all the sensors. So this is the full electronics and servo assembly. And then below this, we'll have the air brakes. So the air brakes is actuated by a linear screw and a stage. And we have a DC motor below it. So the motor will rotate the lead screw and the platform will move up and down, which will push the air brakes in and out. So we also, to support this mechanism, we have four linear rods going through them. So that will provide structural support while the airbrakes are being actuated.
If one of those air brakes fail, do all the rest stop or?
So it's designed such a way that one of them will not fail, but in case they do fail, they will return back to their zero position.
Okay. Okay. That sounds okay. Yeah. Let's hope they don't fail. Let's hope they work.
Yes. So this is all about the controls part. If you have any questions, I'll be happy to answer.
No. No. It looks straightforward to me. Thank
Yeah.
you.
Also, just to touch up on the fail safes, so we have implemented a few fail safes. So in case any of the canards breaks off, we will be able to detect them and bring all the others back to their zero position,
Okay.
just to get rid of any
Yeah.
pitching on.
Yeah. You always have a fail safe.
Yeah.
Okay.
Yeah.
Sounds
Yeah, that's
good.
all about the controls part.
Again, I think I forgot to mention properly about the recoveries part. So here, when it comes to the mechanical links, we would have. I'm going to show the pillar. So here we would be having. So on one side, we would be having a quick link connected to a I bolt. On the other side, we have a U bolt, a swivel link, and a quick link. Those are where the shock cords are attached. and about L by 4 of the shock cord is where the parachute is located. And on this one of the instead of tying the reefing line to the main line, we have tied it to one of the shroud lines of the parachute, and we have also stitched loops in the parachute, and the reefing line goes around that. So the reefing ratio is 1.72. That is, the 12 feet parachute would be constructed to a diameter of 7 feet, and there will be two piranha cutters, tender rocketry piranha cutters that will be there. One will be connected to the cords, one will be connected to our SR avionics, so that just in case one of them fails, the other one fires off. And the whole parachute will be packed inside the deployment bag. And outside the deployment bag, we'll be stitching line stoves so that the shroud lines are properly, neatly packed outside the deployment bag. And yeah, that's about the parachute deployment system.
Okay, thank you.
So, as I mentioned, last year we went with a black core recovery, but this year is the first time we're also trying to implement a carbon dioxide canister based recovery system.
But so you're using one carbon dioxide and one black powder?
Yeah, that's it.
Okay.
Yes.
Okay. Sounds good.
So, if the system so far clear, we'll now dive into the avionics bay and like the flight computer.
Okay.
Yeah.
Hello, Paul. Hope we are audible.
Hello.
Yeah. So, as you can see, this is our avionics bay, and it consists of main components, which includes the. Can you keep it?
You're very faint.
Yeah. Can you see it properly? So,
I can see. I can't quite hear though.
it's very feeble. Can you hear me now?
A little bit, yeah.
Yeah, try talking. Try talking now. Try talking. Yeah, yeah. I connected it to me. Oh, shit.
Hello. Can you hear me?
Oh yes, now it's better.
All right. So this is our avionics bay, and let me show you go through what are the PCBs involved. So this is our SRAT flight computer, and this is our SRAT telemetry PCB. And if you can see here, this is our HOTS altimeter, which is Blue Raven, and
Okay.
and down. So this is our battery bay, which consists of two 6,000 mAh, 12.8 volts lithium ferrous phosphate battery packs, which are BMS included. So when combined, they produce over 24 volts. And if you can see on this side, this little cabin consists of our
Uh, your audio died.
hello, can you hear me?
Now I can. Yes.
So as I was saying, this is our HOTS GPS tracker, which is featherweight, which is powered by its own singular cell. And all these components, as you can see here, are powered by 2s2p configuration of lithium cells. They're housed inside, and these are the wirings that involves them. So when it comes to FC, it has a myriad of sensors, which involves a BMP388, which is an altitude sensor, an ADXL 375, which is a high range accelerometer, and a BNO055, which is a 9DF IMU sensor, which helps us, which has an accelerometer, gyroscope, and a magnetometer, helps us get order angles. So the TNC microcontroller, which implements the flight path logic and also gives us the pressure, temperature, acceleration, and angular velocity data, as well as orientation. So it uses the data from the high range accelerometer as well as the 9DF IMU sensor and combines them using sensor fusion and provides you with orientation and altitude. So when it comes to telemetry PCB,
Yeah, so I'll be taking over here and explaining the telemetry module. Hope I'm audible. Money huge. Yeah. Hello, am I audible, Paul?
Yeah, I can hear you. Yes.
Yes, good. So I'll explain the telemetry PCB now. So the telemetry PCB consists of a ESP32 microcontroller, which receives data from the CAN module and sends the data to the communication module. So the communication module, we are going with a eByte E32 LoRa module. This operates at a frequency of 862 megahertz. And then you have the SRAT GPS here. We're going with the uBlocks NeoSam module. This operates at a frequency of 894 megahertz. And yeah, that's it for the telemetry module. And this PCB right here is the one that controls the valves connected to the engine and the aux tank. And we call it the engine dev PCB. So this again is controlled by a ESP32 microcontroller. And then we have a few buck converters to convert the voltage according to the valve's needs. And we have a MOSFET relay right here, which is used to control the NO valve. It acts as a key switch and controls the NO and NONC solenoid valves. So
Okay.
that's it for the avionics. Do you have any questions for us?
The big battery in there. What is its chemistry? What kind of battery is that again?
So this is a LiFePO battery, lithium ferrous.
Okay.
Yeah, one sec. Yeah.
Okay. Just want to make sure.
Okay. So this is two batteries right here, which have 6,000 mAh and 12.6 volts each. So that comes out to be 24 volts, 24.6 volts in total. Yes.
Yeah, that's fine. Okay.
Any other questions?
No, sir.
Thank you.
So, Paul, should we dive into propulsion right now? Our propulsion system and fuel station.
Yes, can do.
Yeah, sure. So Rohit and Vishnu will take over. Rohit and Vishnu will take over. They will be detailing you regarding our propulsion system. Feel free to interrupt us at any moment to ask the questions that you might have.
Hi, Paul. I'm audible.
Hello.
Yeah. So this is Vishnu. I'm leading the station along with Rohit. So I'll be explaining you the tank part, oxidizer tank part. So the oxidizer tank has three parts, like a bulkhead, cylindrical section, and then another bulkhead. So each bulkhead will be having two ports. The upper bulkhead will have a fill line and then a PT port. The lower bulkhead will have a feed line and then a fill line port. So the upper part, which consists of fill line, it has a PRV, pressure relief valve, and then a normally open solenoid valve. So the PRV opens at 80 bar pressure, and then the normally open solenoid valve will open if there is any power cutoff or anything. So now we'll be showing you the fill line.
Okay.
One second. Vent line. So So along with that, we have a port for pressure transducer over there, which records the pressure readings of the tank and then gives us the live feed as well. Also to mention the materials, this tank is made up of AL6082. The cylindrical section is made up of AL6082, and the bulkheads are made up of AL6061. So this tank is rated for 70 bar. I mean, we designed it for 70 bar with a factor of safety of 2,
and then we tested with 100 bars of continuous pressure for around 5 minutes. So it is leak proof. So each bulkhead will have two O-ring slots, like two O-ring grooves, which will be a leak proof. So as you see, that is the vent line, which consists of PRV, uh, the L section. The L-shaped one is PRV, and then a solenoid wall, normally open solenoid wall. Below that, we have a PT port, which will host the pressure transducer, helps in recording the pressure readings, and then helps in monitoring the pressure readings. So this entire length of ox tank is 900 mm with a OD of 160 mm and then ID of 152. The thickness of tank is of 4 mm, which will be connected to 17 bolts at the top and then 17 bolts at the bottom, which is of M10. Now coming to the bottom of the tank, we have a feed line and then fill line. So feed line is currently of half inch. Uh, it consists of half inch seamless tube sections and then a servo wall, MBB wall, which is controlled by servo. And then coming to the fill line port, it will have a QD, quick disconnect, and then a NRV section, non-return wall. Currently, we'll be showing you the feed line and then fill line.
Okay.
So, to mention the capacity, it is of 15-liter capacity. The tank is of 15-liter capacity. Along with this, we have a quick disconnect housing, which will helps us to disconnect after the filling. Can you just show me the quick disconnect section to the cam? To the cam.
It's actually the filling.
One second. So as of now, if you have any doubts, you can ask me. Paul, now we'll be explaining you the fill line. So, I'll explain. So the fill line consists of NRV, non-return wall, and then a needle wall. After that, a pressure transducer port, and then PRV, pressure relief wall, and then a manual vent line, which has a needle wall over there. And then to vent using power, we have a normally open solenoid wall. And then to fill and to control the flow, we have a normally closed solenoid wall. So this is regarding our fill line. So if there is any power failure, the normally closed one will remain closed, and then the normally open will remain open, and then it went out the entire tank. So to the connection between the fill line and then to the tank, we have a quick disconnect mechanism, which which will have a linear actuator, and then a female end of quick disconnect section. Female end of quick disconnect. As you see in the cam, that is the female end of quick disconnect system, which will be connecting to the male end of fill line in the tank. So the linear actuator helps to disconnect after the filling. I hope you are clear with the fill line.
Yes.
Yeah. So now I will be showing you the feed line and then the fill line in at the bottom of the tank. So as you see, we have a manually motorized ball valve, which is controlled by servo. The ball valve, which is controlled by servo, which is of half inch. All the seamless tubes are half inch. And then this half inch section is connected to the injector bulkhead of engine.
Okay.
Now, and then we have
I mean, at the bottom port, we have one more port for filling, which will be having a male QD system, and then a swell elbow, and then NRV, non-return valve, to
Okay.
prevent the backflow after filling.
Yep.
Yeah. As of now, do you have any doubts regarding the fill line and then the tank? You can ask me.
I don't have any questions right now.
Okay. So now, Ashish will be explaining you about the engine part.
Hello, Paul. I'm audible. Right. So the engine here. Okay, we'll start off with the injector bulkhead first. So the engine bulkhead we are using bolt designs in both of our bulkheads. The injector bulkhead has flanges which will connect to the longerons, which are going to be the load-bearing members, and this is going to be transferring the thrust from the engine to the actual airframe. And we are also using a half-inch injector design here. And as you can see, we have two pressure transducers for data acquisition as well. One will be pre-injection and one will be post-injection to get the injection pressure difference and the pressure drop across the injector. And the injector plate design that we are using here, it's a customizable design. So we can implement any design that we need, and we will just have to bolt the injector plate onto the injector bulkhead. And as you can see, there's in between the smaller injector holes and the bolt holes, there's a O-ring groove, which is to leak proof the actual injector plate and the flow. And also, we have implemented a kind of a swirl design in our injector plates. So the holes which you see are radially 10 degrees rotated in such that half of the holes are clockwise and half of the holes are anti-clockwise in the anti-clockwise direction to induce a swirl effect and enhance atomization of the liquid N2O that will be injecting. And do you have any questions?
No, that looks good.
Okay. Right. So we'll move on to the the nozzle bulkhead. My bad. The nozzle bulkhead to accommodate the boat tail has threads on it, and again we are using the similar kind of bolt design here. We have not bolted. We have not attached the bolts as of now. If you would give me 2 minutes, I will show you the nozzle as well.
Yes, can do.
Yes. Meanwhile, if you have any questions regarding the verticals or anything,
Nope.
right. So I would also like to brief you about the thermal insulation that we are using inside the engine. We are using a phenolic-based thermal liner between the actual combustion chamber and the aluminum casing. Moreover, talking about the fuel that we're going to use is going to be 400 mm lengthwise, radial port of 60 mm, and yes, we are using a paraffin-based design. And we are using our own patented design, accommodating something called EVA, which is just to provide. Okay, my team member is also sharing screen now. We are going to share the cross section of the actual engine. Right. So I was talking about the additives that we have added into the fuel. So EVA is there just to provide structural integrity to so as to prevent clogging from happening. Are you able to view the camera right now? Is the view clear?
Yes.
Right. So we are using a graphite based nozzle in our design. Then it has a expansion ratio of 6.92 if I remember correctly, and uh, it has a throw dia of 35 and a design pressure of 35 bars. Um Right now, the nozzle that we are showing you was used in a static fire. The lip of the nozzle is broken. We are going to use, we have given two more sets of nozzles for manufacturing, which we are going to take for the competition. And the nozzle is going to be fit inside and held inside with the boat tail. So, okay, that's right. So we'll move on to the cross section of the engine. Before that, I would like to ask you if you have any questions before I move on.
Oh, go ahead.
Right. So in the engine, we have implemented a pre-combustion chamber and a post-combustion chamber as well. Another highlight of our engine would be the igniter puck that we are using. It's RNX-based propellant, which we are using to ignite our engine and heat up the oxidizer flow and sustain the flow as well. So we have a initially, you can see here that we have a 65 length of pre-combustion chamber. After that, we have a RNX propellant grain with an ID of 50 again RNX based. After that, we have the fuel grain with an ID of 60 an OD of 100 and a total length of 400 After that, we have implemented a post-combustion chamber of 110 length, and as you can see in the blue color here, yes, the blue color, uh, it's my bad. The post-combustion chamber is 160 and the ID of the post-combustion chamber is 110 Right. So the blue colored part is the phenolic part, which is the thermal liner that we are using. And to create a pressure seal, again, we have implemented a primary and secondary OC groove design into the nozzle end. The nozzle has, right, it has, if you can see it, there's a phenolic lip that fits into the nozzle, which is going to be the pressure. Uh, right, if you can see in the camera, there are two O-ring grooves that would go into the hilum lip to create a pressure seal in there. And towards the injector bulkhead, we have also implemented a head end phenolic head end, which would go on and again create a pressure seal with the hilum casing and with the injector plate.
Okay.
So, right, and I've covered most boat tail. Right, the boat tail, the nozzle, the boat tail is going to be, uh, as you can see it on the engine, it is going to be the load bearing for holding the nozzle inside. We're going to use the boat tail to hold the nozzle. Right. Hold the nozzle in the engine itself, and right, the boat tail is also going to help us center the engine with the airframe. The shoulder is going to be the shoulder fits with the ID of the airframe.
Okay.
So we'll show you. Right, so we would like to show you the data of a static fires. Right, so this was the chamber pressure that we were able to achieve in a static fire. The spike that you see there, we suspect is because of the igniter breaking up and clogging. We have implemented measures to prevent that.
Okay.
You can see. Can you move on? This was the chamber pressure, and this was the thrust that we were able to achieve, an average of 1 kilonewton. But however, this was with a half inch feed line with check valve. We realized the check valve was causing drastic drops in the mass flow rates. So we have removed the check valve, and we have conducted another static fire without the check valve. So is there anything else? Right, this is the pressure in the oxidizer tank. The pressures, move on, mass. That's all. Did you have the thrust? Just give me 1 second, Paul.
Okay.
Well, we'll share the footages of the static files we've had so far. We'll share our screen and we'll show you the footage. We static file the engine twice. We'll just share you the footages. Paul, can you see my screen?
Okay, now I can see the fire, yes.
Yeah. I'll be starting the footage. Right. Could you catch the audio, or like was the audio missing?
I caught a video. It didn't look like it ran very well.
Oh, okay. We'll also show you this was the footage of our second static firing, which happened recently. We'll also show you the footage of our first one. After the meet, we'll attach all these videos and also share you the drive. We've done a lot of tests, including for pressure for our tanks and then like for static fires. So after this meet is done, we'll share you a drive link with all the footages. Same thing again. Do you want to have the same with the audio ones? Uh, yeah. Can you guys order right now? Yeah, so I'll show you the first footage right now. The first static firing. Can you see my screen now?
Yes, I can.
Yeah, so this was for the first static fire. That's IREC going out. Yeah, just give me a second. So, if you have any questions and anything so far, you can feel free to ask us.
What kind of data did you get out of that long burn?
So, like the static files, you mean, right? We got the pressure from the static files, like pressure and thrust.
Are you asking me a question?
No, I was mentioning that we got pressure and thrust from the static files.
Okay.
We got an average thrust of around 1 kilonewton so far. Like Assis over here might be able to explain it better.
So in the second static fire, we were able to achieve average thrust of 670 newtons, which uh, which was because we, due to some delays in the testing, we were only able to test it in later in the evenings, where the pressures dropped drastically, because of which we weren't able to fill the oxidizer tank, because there was no pressure difference between the fill line and the oxidizer tank.
Okay.
But in first firing, where the temperatures were way higher, we were able to achieve higher pressures, better mass flow rates, and we expect drastic improvements because of the removal of the check valve. However, we weren't able to test that because of the conditions on the day of the testing.
Okay. So are you going to try to run a static fire before you
Yes,
come to
yes, sir. Yes, sir. Yes, sir.
Okay, so if you do that, then all I need to see what your test results are. You know what your performance data is. Make sure that you've got a good performing motor.
Sure.
And it matches pretty close to what you put down on your design.
Sure,
Okay.
sir. Understood.
Yep. You're scheduling that, I guess, in the next week or two?
Yes, sir.
Okay.
We are going to attach whatever data we have right now. We are also indeed going to try for another static fire, and we will get back to you with the data of the next static fire as soon as it happens.
Okay. And the only other thing that I need right now is when you get finished when you finish with your fin can, with all the wrap and everything else that you need to do, then just send me a picture of the fin can. Okay?
Sure, sir. Will do.
Okay. Okay. Sounds good. Okay. Anything else?
Any recommendations from your end, Paul, on any module of the rocket so far, or like?
No, nothing right now. I mean, the rocket looks pretty good. Everything looks pretty, looks to be in pretty good shape. You know, you gotta, we've already discussed that we need to get a better static fire.
Yeah.
Everything else mechanically looks good. So I may have a question later on, but I can do that over the mail.
Got it. And another clarification that I require is on the mail you mentioned that we can get a crate from ESRA on second, right? We can the crate in which the rocket is gonna go, the shipping crate, the shipment.
Yeah, the shipment. You want to get it on supposedly the event director, Mrs. Taylor, Stephanie, she says that she can talk to them and see about getting you guys access on the second. They're going to generally open it up for the 5th, but she's gonna work on getting you guys access. So I'm not going to be there. I won't be there until the 7th. Who's going to be the guy in charge of picking that stuff up? Is it going to be Aaron? Who's going to pick it up?
I'll be picking the stuff up. So if you can on the mail thread, if you can connect us to like the in charge from the other end, this Stephanie whom you're mentioning about, we'll try to be in contact with her and we'll request her regarding the same. Because getting the crate on second is crucial for us. We'll have the time to work on our rocket.
Yeah, I understand. So I will pass on your name to her and tell you to work with, or tell her to work with you on verifying that. And I'm not sure she's going to be on there on the second, but so she's going to have to coordinate it with the warehouse, and you guys are going to have to, when you get to the warehouse on the second, we'll try to make sure that your name at least is on the pickup order, so that and put it on the bill of lading on the crate. Attention, Gagan or whatever. Okay.
Yeah.
And then they'll know, okay, that's your crate, and you're there to pick it up. Okay.
Sure. Thank you for that. I'll just write a mail to you again on this, like on just pushing us forward for the crate.
Do what? I'm sorry.
I'll just write a mail again on the same to you as well. If you can forward that to Miss Stephanie, that'll also be great.
I didn't understand you. I'm sorry.
Addressing the same issue, I just write a mail to you that like getting a crate on second is crucial for us. If you can put a word forward as you mentioned, that'll be great. Thank you for that.
Okay. Yeah. We're working it. We'll make sure it gets done. Okay.
Thank you.
Okay.
Hello,
Other,
Paul. Am I audible?
yes, sir.
Yeah, I just have one question. So, what should be the minimal safe distance that you would recommend us to have between the rocket and the fill station?
The ground station, the control station, has to be 1,500 feet away. So you have to have good wireless uh, access for 1,500 feet. Okay? And 1,500 feet is 5,000 meters. Or no, not 5,000, 500 meters.
I would like to clarify that it's not about the ground station; it's the fill station and the rocket.
The fill station. Well, the fill station, everything there is going to be located. When you put your rocket on the pad,
Hmm.
when we assign you a pad, I only have two pads, and I think five teams using them. So everybody's sharing a pad, just like you did with the solids. But when you're ready to launch, you've got everything rocket ready to go, and all your plumbing's ready to go. Then we'll assign you a pad. You'll set up your rocket, set up your ground station right next to it, and we'll get you ready to go. Um, so the tanks will be there. I've already got the confirmation that the tanks will be there. So we can work all that out when we do the setup. Um, uh, we could talk about it when I'm doing your safety inspection in Midland, and uh, if I get all the safety inspections done on Monday, then it's more than likely I'll be out at the launch pads on Tuesday. Uh, and then you're welcome to come out there when you're done with your stuff in the on the Tuesday sessions. Or you can have somebody come out, and then we can walk over and take a look at the pads and everything, and figure out what we need to do. Okay. But we can coordinate all of that on the 9th of June on the Monday. Okay.
Yeah, got it. And also, follow-up question: can you please brief us on the support system so that we can mount our load cell on which the rocket will be
Uh,
resting?
yeah. You're talking about the load cell for the weight of the rocket.
Correct.
Um, I've got two different pads. One's it's got a truss on it. The other one is just a standard mast, similar to what you flew on your solid rockets. Um, I can sit there and take some measurements. If you come out with various ways to clamp it on the pad, I'm assuming you're going to have it. Uh, that send me a picture if you can, or a diagram of the relationship of your load cell to your rocket uh, when it's mounted on the pad, so that I can look at it and see how it will match up with the two pads I have. Because it's hard for me to tell. Uh, I need to see your load cell interface to the rocket, where it's going to rest and everything else, and then I can turn around and determine how we're going to mount it to the launch pads. Okay.
Yeah. And final question from my end.
Okay.
When we explained about the fill station, we mentioned about a fail-safe mechanism of using solenoid valves. My question is, as a backup of solenoid valves, we are planning an alternative of using motorized ball valves. Would that be fine? Will we be able to clear FSR?
Uh, I'm
You
not sure I got Why don't you say that again to me, please?
Yeah. So, can you show the camera there in the station? Am I audible now?
Yeah, I can
So
hear
as you can
you.
see in the field station, so we are using making use of two solenoid valves as a part of fail-safe mechanism. So what happens in solenoid valve is that in case of any power failure, the NC valve in the fill line will automatically close, shutting down the oxidizer flow, and the NO in the vent line will automatically open, venting out the oxidizer. So during our recent testing, we are finding few issues with the solenoid valves, and if it persists in the US as well, we are planning to replace it with motorized valves. Is it fine? That's my question. Replace a
Wait.
solenoid valve with motorized valves.
Oh, you're talking about using like a motorized lever.
Correct.
Is that what you're talking about?
Using a what symbol?
Like a lever arm?
Control valve, not a manual valve, but a servo control valve.
Which can be accessed remotely. It's a servo assist valve.
Uh, I would have to see. I would have to see a picture of what you're thinking about using, just to
So this is the kind
verify.
of valve that I was mentioning. So we have a
Okay.
valve here that is actuated by a servo motor.
Oh, so you're talking about having one that has an integrated motor.
Correct.
Okay, yeah, that'll be fine. Um, Now that is your fill valve that you're thinking about motorizing.
Yes. That can still be
Um,
activated remotely using a telemetry module.
yeah. Uh, if you have an issue to where you got to turn it off and that thing is left open, um, is there some way to turn off the fill tank without that, or because I don't? The only thing I don't want this thing to do is if you open it up, but then it dies. How is it going to auto close?
Yeah,
How is
yeah,
it
that
going
is
to auto?
one thing to worry about. But since we're using battery pack systems, I don't think there should be any power failure to be worried about. We have telemetry people who can explain you better with that.
Okay.
Manish?
I need to think about this. Um, yeah, I need to think about this. I'll I'll get back with you. Or get back with you or Aaron or Don, either one.
Okay, so thank you. Got it.
Yep. Okay. Yeah, I've got it on my list.
Yeah, yeah, Paul. From our end, that's it for the moment. Thank you for the review. If you have anything else, you can ask. Else, I think we can conclude the session for the day. If that's fine.
Uh, Hello. I caught
Can
half
you
of
hear
that.
me? Can you hear me, Paul?
Yes, I can hear you now.
Yeah, yeah. Those are the questions we had from our end. If there's anything else, I'll drop you an email asking for them. If you have any questions for us, you can feel free to ask us. We'll love to answer them. Uh,
Yeah.
or else,
I'll,
I think you can conclude the meeting.
excuse me. I'm sorry.
Like these are the questions we had from our end, and like the answers for them we got. If there's anything else, I'll write you an email asking for the same. If you have any questions for us, we'd love to answer. Or else, I think we can conclude the meet.
Okay. Okay. What? One question is probably a little too late. Did you record this meeting?
Yeah, yeah. So we are recording this meeting.
Oh, okay. Okay. Good. Because
Yeah.
If I didn't ask and then my boss came back at me, did you have a record of that? I don't know. So, okay,
Yeah.
good.
Yeah.
Other than that, yeah, I think we're good for now. I'll probably be talking to you in the next day or two. Okay.
Sure. Sure. Thank
Okay.
you.
Thank you very much for having your team
Yeah.
talk to
Thank
me
you
about
having us.
the
Thank you for the review.
project. Okay.
Thanks for the
Bye.
call. Bye bye. Good night.